The next two pages, we're going to be talking about theory, and I know how everyone loves theory, but this theory is going to be really helpful. Trust me. We're going to use that bell shape to our advantage. So topic 13, normal approximation for the distribution of p hat. Remember, p hat is the sample proportion, so it's based on sample. So example 13.1 coin tosses. Now you could do this in the applet. I've actually printed out things from the applet, so we'll talk about those as we go along. Suppose we look at 1,000 repetitions. So in other words, in each down here, each of these has 1,000 dots total in each of these. Each of these has 1,000 dots total. It's hard to see the dots individually, but this one's a little bit clearer. You can see there are dots. With either 10 coin tosses, this first one, that's A, 100 coin tosses, B, and then 500 coin tosses. Each time we record the number of heads and proportion of heads and graph the distribution. So you'll notice that this first row here is by number of heads, and the second row is by proportion of heads. You'll notice that the y-axis also is not labeled. I would label this either count or frequency, in other words, how often it happened. So there'd be a dot, like you can tell that for here, the average or the center, I would say, is right at 5, about 5. Looks pretty symmetric too. If I ran the applet again, do you think I would get exactly these same charts, these same graphs? What do you think? And hopefully you think no, because samples vary, and that's something we want to keep in mind. So I said count, you could also call it frequency. You may have seen it labeled as frequency. Either one of those would be fine. Remember, this is going to be the max if they were all heads, and that did not happen on this one. You're going to notice as we go up in terms of sample size that, whoa, we get nowhere close to 100 heads. Remember we talked earlier in this course about how when you have more questions, it's easier for me to see that if someone is guessing or not. Same thing here. If you only have 10 flips, yeah, you could get 9 or 10 heads, but if you have 100 flips, what would be the odds of getting 99 or 100 heads in a row? It's pretty low. And same idea as we go up to 500. Remember, each of these dots in here is a p hat, and samples vary. Each dot, once again, is a p hat, and it is the result of one of the 1,000 trials that we did in each of these scenarios with either 10 flips, 100 flips, or 500 flips of coins. Now we have two rows. We have the number of heads, and we also have proportion of heads. We're going to focus on the proportion of heads here. Focus on part A, focus on the dot plots of the proportion of heads. What do we notice about the following features of the different distributions? So, the means. Where would you say the means are, roughly, looking at each of these? Blow it up a little bit. And hopefully think, well, they appear to be right about in the center. So the means are around 0.5. And that happens to be the value of P. Because remember we said that looking at a coin, 50-50 coin, what happens to the standard deviations as n goes up? What happens to our standard deviations? Well, here, remember, standard deviation is a measure of spread of the data. Here, looking at the proportion of heads, it's easy to see. We go from, let's say 10% up to 90%, or 0.1 to 0.9, whereas here, the spread is much less, all right? So what happens? The standard deviation goes down as n goes up. As n increases, we notice that as n goes up, so looking from left to right, we notice that what we see, it looks more filled in. The graph looks more normal. It looks more filled in. There are less gaps. So we're moving from discrete towards looking more continuous. Okay. Now it says here, for which scenario does the shape of the distribution of proportion of heads appear more symmetric and continuous compared to the others? And we just talked about that as we were going along. And just to go back to it for a moment, to me, it's here. in this case. I'll just circle the whole thing. For this one, that's where it looks the best. So what can we say? First of all, the shape, talking about that, as n goes up, the shape looks more continuous and bell-like. Oops, sorry about that. What do you notice about the values of NP and n times 1 minus p for these scenarios? Let's calculate it. So I'll call this number 1 here for this part, and I'll call this number 2 this question. We're going to do n times p. In this case, it happens to equal n times 1 minus p. Why can I say that? Well, because p is 0.5. Okay, so I'm just going to do n times p for each of these just because it is equal. So for A, for the first one, I'm going to get 10 times 0.5, and that gives me 5. And that's for case A. Going back up here, A, we had sample size of 10, and P is 0.5, and of course, P is not going to change. For B, we have for n times P, we have 100 times 0.5, and we end up with 50. And finally, for C, at 500 times 0.5, we get 250. So what's happening as n goes up? Well, this value also increases. Okay, makes sense. This leads us to a central limit theorem. This is one of the fundamental theorems in statistics. Thus, sample proportions have a predictable pattern. Okay, so it's predictable. When random samples of size n are taken from a large population, and we'll discuss what large is in a moment, the sampling distribution of the values of the sample proportion calculated, p hat calculated for the samples has the mean of p and a standard deviation of the square root of p times 1 minus p over n, where p is that defined population proportion of success. We were doing a coin, so p is 0.5, and everything is going to be 0.5, and hopefully you think, no, it won't always be that way. Also, the overall shape of the distribution is approximately symmetric and bell-shaped, in other words, normal, if the number of successes and the number of failures both have to be at least 10. So we're going to need to check that as we go along if we're asked, can we use the central limit theorem to our advantage? The population is considered large, so we have a large population if it's at least 10 to 20 times the sample size. Well, you may be saying, well, how am I going to use this? And we'll get there in a moment. But let's first of all verify that this makes sense. We know that let's look at n equals 100. If we go back up to n equals 100 here, and this is based on running the applet, we see that the center is at 0.5. Okay. By the applet, we have the mean is 0.5, and the standard deviation that's given to us, and that is listed, was 0.047. This is based on the applet. It did the calculation for us. These are our summary statistics here. If I ran it again, would I get exactly the same standard deviation? No, because remember, samples vary. Okay, so we've seen this many times as we've been going along back to when we were dealing with Sarah. All right, now let's see if the value that we get here and here are close. So using that central limit theorem, let's see what we get. The mean is p, which is 0.5. Perfect. Now the standard deviation is going to be p times 1 minus p over n, and we take the square root. So let's see, we've got 0.5 times 1 minus 0.5 all over n, and n in this case is 100. Take the square root, and we get 0.05. Are these two close? Yeah, they're pretty close. Are these two close? Yeah, they actually happen to be identical. So, can we use that central limit theorem? We're going to see an example of how it works in just a moment.